Hi guys, this video is for 2.5. We're going to look at the derivative of a few trig functions. So this table is directly from your textbook. The big two that you guys are going to want to memorize are those first two. So the derivative of sine is cosine. The derivative of cosine is negative sine. Okay, so those are going to be the two big ones. Here's some other ones here that we're going to use in practice. Those first two you definitely want to commit to memory. Okay. So let's first prove why. Let's just do this first one. Why is the derivative of sine x cosine x? So we're going to use our definition of a derivative, the difference quotient. So we're going to look at the limit as h approaches 0 of sine of x plus h minus sine of x over h. Okay, so we're actually going to use a trig identity here. We're going to use the addition identity for sine. So remember this, sine of a plus b is the same as sine of a cosine b plus sine of b cosine of a. Okay, so we're going to treat x as the a and h as the b here. Okay, so I'm going to split this using our addition trig identity for sine. So this turns into the limit as h approaches 0 of sine x cosine h, okay, plus sine h cosine x minus still that sine x all over h. Okay, so what I'm going to do here is I'm going to kind of strategically rearrange some things, you guys. So I am going to break this into two fractions, but I'm going to just move this guy over here. So we're going to do the limit as h approaches 0 of sine x cosine h minus sine x over h. Okay, and then plus we have sine h cosine x over h. Okay, so on this one, I'm going to factor out a sine. So we still have the limit as h approaches 0 of sine x times what I'd be left with here is cosine h minus 1 over h. Plus, same thing, I can take, I've got sine h over h times cosine x. Okay, so why is that helpful? Well, these are two limits that I know as h goes to 0. So this limit is 0. This is back from chapter 1. Okay, so the limit as cosine of something minus 1 over that same something is 0. Sine of h over h is 1. Okay, so we are finding those limits. So I have now sine x times 0 plus 1 times cosine x. Okay, so if I were now I don't even need to plug in h, right? Because all my h's are gone. But here's what I have left. Sine of x times 0 is 0 plus 1 times cosine of x is cosine of x. So that's why using our definition of a derivative, the derivative of sine is cosine. Okay, that's just to show you where it comes from. There are some proofs for those other ones in your book as well. So if you want to take a look, you're welcome to. We're just going to prove the derivative of sine's cosine for now. Okay, so we're going to use that now to find some derivative functions. So we're going to find y prime. Okay, so derivative of x is 1. And then we have 4 times, I guess I'll write this out so you guys can see this part. So we've got d dx of x plus 4 times d dx of sine x. That's really what we're doing. Okay, so the derivative of x is 1. Then we got plus 4, derivative of sine we just proved is cosine. So there is our y prime. All right, this guy, we're going to use that derivative we just found, but we're also going to use the product rule. So here's like the f and the g that we can apply the product rule to. So we've got y prime is equal to f prime, which is going to be 2x, times g of x, plus f times g prime, which is going to be cosine x. And again, you can leave it just like that. So we're just applying the product rule there to get the derivative. All right. I'm going to zoom in just a hair more, you guys. Okay. For this next one, we have sine x over x, so we know the limit of that is 1, but what is the derivative? So I'm going to use my quotient rule, and I'm going to treat the top as the f, the bottom as the g, so y prime would be f prime, so cosine of x, times x, g, minus f times g prime, which is going to be 1, okay, all over g squared. Okay, really the only thing I might rewrite is I might just put that x in front so we don't actually think that is an x squared, so I'd probably write it like this: x cosine x minus sine x over x squared. Okay, example 4. Same thing, I'm going to use the product rule. Here's my f and my g. So y prime is going to be e to the x times sine x plus e to the x still, and then derivative of sine is cosine. Again, if we want, I could factor out the e to the x and also write it like this. Either would be acceptable. If I were finding like the second and third derivative, this just makes that next step a little bit easier. Okay, 5 is also one I can use the product rule on. So here's my f, here's my g. So we've got f prime would be 2x. And then plus derivative of cosine is negative sine. This is one of the ones on the table on the previous page. Okay. And so then, yep, okay. So same thing, I might just simplify to get rid of the parentheses there. So we got 2x cosine x. Negative sine is going to change this guy to x squared sine x. Okay? All right, cosine. We're going to use our quotient rule. Cosine is my f, 1 minus sine x is my g. Okay, so f prime is going to be negative sine x times g. Okay, minus f times g prime. So I'd get 0 there, and then that negative would make that negative cosine. Okay, all over g squared. Okay, we can do a little bit of simplifying because I actually am going to get a Pythagorean identity here. So if I distribute that sine x, we get, let's see, negative sine x plus sine squared. And then negative cosine times negative cosine is positive cosine squared. So remember, sine squared plus cosine squared is 1. So I can treat this as 1 minus sine of x. And why that's helpful is because then I can actually cancel one of those with one of those. Okay? And then we are going to end up with 1 over 1 minus sine of x. So that would be just kind of a more simple. So then again, if I had to find like second or third derivatives, this one becomes a lot easier if I've simplified, combined like terms, cancel things where I can. Okay, 7. Find f prime if f of x is secant of x. Okay, so again, previous table, so secant of x, okay, the derivative of secant is secant times tangent. Okay, so they want us to find the second derivative, so we got to find the first one first. So the first derivative is secant times tangent. So we just got that from the table on the previous page. Okay, so now to find the second derivative, we got to use the product rule. So we're going to say, so here's f, so f prime again would be secant tangent times g, there's our g function. Okay, plus f times g prime. So the derivative of tangent is secant squared. All right, so what can I put together here? Well, the furthest I went, you guys, is I just combined these guys and these guys. So we've got secant x times tangent squared of x plus secant cubed x. Okay, so that is the second derivative of secant of x. We could also be asked for something like this, you guys. We could be asked to find a certain value given a derivative. So if I did this one, for example, f double prime of pi over 4, now I just substitute pi over 4 in for all those x's. So if I were to find, we'll go ahead and do that as an example. Okay, so secant of pi over 4 times tangent of pi over 4 squared plus secant of pi over 4 cubed. Okay, so secant of pi over 4, if you guys recall, is root 2. So I'm going to get root 2. Tangent of pi over 4 is 1. And then root 2 cubed. Is that what I want? Okay, so root 2 cubed, if you think about root 2 cubed, that's the same as, sorry, I just want to do this part. So just to make that make sense. So root 2 cubed is the same as root 2 squared times root 2. So 2 root 2 is another way I can think of that. Okay, so root 2 times 1 plus 2 root 2 is going to give us 3 root 2. All right, so again, that's just if we're asked to find a particular value at that value given a certain derivative. All right, last, or we're close, very close. Find all points on the graph of f of x equals x plus sin x where the tangent line is horizontal. So remember, the tangent line is horizontal when my slope of the tangent line is 0. So remember, the slope of the tangent line is the first derivative. So we want to find where is f prime of x equal to 0. So let's find f prime first. Okay, which is going to be 1 plus cosine of x. So we're going to set that equal to 0 and solve. So we got negative 1 equals cosine x. So I'm asking myself what angle or angles give me a cosine of negative 1. So if we think unit circle, cosine is negative 1 right there, right? That happens at an angle of pi. So we would say x is equal to pi, and then we could go around the circle multiple times. So we could say plus 2 pi k. So pi and then any multiple of pi would also give us a tangent horizontal line, or horizontal tangent line. All right, here we go. Now we're on the last one. Simple harmonic motion. Okay, so this can be used for pendulums, for springs. These are things that can be modeled with trig. Okay, motion that can be modeled with a trig function. So we have this spring that's hanging, okay, and in its equilibrium position, the spring is 2 meters long. So without being stretched or compressed, okay, 2 meters long is equilibrium. If the object is pulled down 1 meter and I release it, it's going to continue to oscillate up and down. So that's going to be that periodic trig motion, okay? The length L of the spring after t seconds is modeled by this function. So this is kind of my position function, the length, okay? How does the length vary? So we know that the original function, or excuse me, the original spring, right? I'm just going to look at this cosine of t. So we know cosine of t lives between negative 1 and 1, but that's not my function. It's 2 plus cosine t. So I'm going to add 2 to all 3 parts of my inequality so that my middle matches my equation. So I've got 1 is less than or equal to 2 plus cosine t is less than or equal to 3. So this function lives between 1 and 3. So the spring varies between 1 meter and 3 meters. Okay, find the velocity. Okay, so this again is kind of like position. So velocity, remember, is the first derivative of our position. So we're going to find velocity of this time, which again is the first derivative of this L function. So if I were to find the derivative of this, so derivative of 2 is 0, derivative of cosine is negative sine of x. T, sorry, keep my variable the same. Negative sine of t. Okay, so there is my velocity function, negative sine of t. All right, at what position is the speed of the object a maximum? Okay, so remember, speed is the absolute value of velocity. So we want when is my velocity at a maximum? All right, so velocity, okay, same thing. We just said the velocity is negative sine t. So remember, velocity is negative sine t. If we were to take the absolute value of that to get speed, we would get the absolute value of our velocity is the absolute value of negative sine t, which is the same as just the absolute value of sine t, right? The absolute value makes it positive. And we know sine lives between, we'll come back to this, right? We know that's true, which means sine lives between negative 1 and 1. So the max I can get to is negative 1 or 1, those speeds, right? Because we're saying this was our velocity, and the velocity, its maximum is 1. Or negative 1, because if I put that in there, the absolute value would give me the same result. So basically, we're asking, the spring is the fastest, the velocity is at its maximum, when sine of t equals either positive 1 or negative 1. Now, when, I'm going to think unit circle again here for a second. So sine is 1 up here, and it's negative 1 down here. So when sine is 1 or negative 1, that's the same as when cosine is 0. So both of those instances, cosine is 0. So why is that helpful? Well, remember, cosine of t, here was my original function, right? If this part is 0, then L of t equals 2 is when my velocity is at its maximum. And they asked what position. So this would be at 2 meters, which remember, that's when it's in its equilibrium position. That's actually when the velocity is at its maximum. So we could say, sorry, I kind of got a little off. We can say velocity is at its max when the position of the spring is 2 meters long, or we could say equilibrium. All right, so kind of just wrote that out in words. The velocity is at its max when the position of the spring is at 2 meters, which is its equilibrium position. Okay, find the acceleration. So acceleration is the derivative of velocity. So A is the derivative of velocity. So the derivative of negative sine is negative cosine. Okay? At what position is the acceleration equal to 0? So let's set that equal to 0. 0 equals negative cosine of t. Divide by negative 1. Okay, so where is cosine 0? Cosine is 0 at 0, if we think about the unit circle. Okay, and again, when t is 0, that is when time is 0, our spring is also in equilibrium. So its position when acceleration is 0 is equilibrium. When, again, cosine of t equals 0, I actually don't even want to put this to you guys. I'm just going to leave it. Well, that is us. We'll leave this. But again, back to this part. If I look at my position function, L of t is equal to 2 plus cosine t. But again, if I want this part to be 0, then I'm left with just L of t equals 2. So that's the position in which the acceleration would equal 0. So the spring, or we can say the acceleration, is equal to 0 when the spring is 2 meters long or in equilibrium. Okay? All right, that's it for our 2.5 video.